Great minds of humanity, celebrating human brilliance.
In the final years of his life, Isaac Newton sat beneath wavering candlelight surrounded by prisms, coins, and unfinished manuscripts, a man celebrated as the master of nature yet still haunted by questions vast enough to keep the night itself from closing around him. Behind the familiar legends of the falling apple and the lonely genius stood a far stranger figure, secretive, suspicious, brilliant, and relentless, someone who could read the heavens with unmatched clarity while struggling to live peacefully among other human beings. To understand how one English scholar reshaped mathematics, physics, astronomy, and even the machinery of empire, we have to follow him from a quiet farmhouse in Lincolnshire to the center of a revolution that changed how humanity sees the universe. Newton was born into a century when old authorities still spoke in the language of Aristotle. Planets seemed to move according to separate celestial rules, and many educated people believed the world could be described without ever fully uniting earth, sky, motion, and light. What Newton achieved was not one isolated discovery but a new framework of thought, showing that the same hidden order could govern an apple dropping through orchard air, the moon circling Earth, and the paths of planets around the sun. Yet the man behind that order was no serene marble sage, because he guarded his ideas obsessively, carried old wounds from childhood, plunged into theology and alchemy, and turned intellectual disagreement into feuds that could last for decades. His biography is therefore more than a tale of genius, because it reveals how loneliness, discipline, ambition, fear, and imagination can combine inside one mind until private obsession becomes a public turning point in the history of civilization. Isaac Newton entered the world at Woolsthorpe Manor in 1642, 3 months after his father died, so small and premature that relatives doubted he would survive, while civil war loomed over England and uncertainty framed his life from the very beginning. When his mother remarried and moved away, leaving the young boy largely in the care of his grandparents, Newton absorbed a deep sense of abandonment that later surfaced in the fierce self-containment, resentment, and hunger for control visible throughout his adult life. As a child he transformed solitude into invention, carving sundials, building miniature mills, studying winds, drawing mechanical contraptions, and watching the changing sky with the patient intensity of someone already trying to decode patterns that other people scarcely noticed. At the King's School in Grantham, where he lodged for a time near an apothecary's household full of tools, bottles, and books, competition with other boys awakened both his academic ambition and the disciplined habit of learning by close observation. In 1661 Newton entered Trinity College, Cambridge, as a subsizar of modest means, serving wealthier students while officially studying a conservative curriculum, even as the great new ideas of Descartes, Galileo, Kepler, and others were beginning to crack the old intellectual walls. He copied arguments into notebooks, challenged established doctrines in private, and filled his famous waste book with experiments in mathematics, because he sensed that beneath confusing motion and changing forms there might exist a deeper language precise enough to capture reality itself. During these student years he pushed toward infinite series, generalized the binomial theorem, and began shaping the method later called fluxions, not as a polished public system yet, but as a set of mental tools sharp enough to cut through problems others could barely frame. While Cambridge lecturers repeated inherited formulas, Newton worked alone in his chamber by window light and candle flame, teaching himself to think with such intensity that isolation ceased to be a weakness and became the furnace in which his intellectual confidence was forged. Then in 1665 the plague closed the university, sending Newton back to Woolsthorpe, and what looked like interruption became one of the most fertile retreats in scientific history, because the young scholar suddenly possessed time, privacy, and complete freedom from academic routine. In rooms lit by daylight from small lattice windows, he passed narrow beams through glass prisms and discovered that white light was not pure at all, but a mixture of colors already hidden within it, waiting for experiment to reveal their separation. During the same period he advanced his mathematics, investigated circular motion, and asked whether the force pulling objects toward the ground might also reach upward to the moon, bending its path continuously so that falling and orbiting became parts of one idea. The apple story, remembered later in life, matters not because a fruit magically delivered a finished theory, but because it captures Newton's habit of turning ordinary events into relentless questions about distance, force, curvature, and the architecture of unseen causes. Historians would eventually call these his wonder years, yet the real miracle was not sudden inspiration alone, because Newton still had to test, calculate, refine, and protect these insights before they could emerge from private notebooks into the shared knowledge of the world. When Cambridge reopened, Newton returned with discoveries few around him could yet understand, and in 1669, still only in his 20s, he became Lucasian Professor of Mathematics, occupying a prestigious chair while remaining temperamentally wary of publicity and exposure. To prove the power of his optical work, he designed a reflecting telescope that used a mirror instead of a lens, reducing color distortion and giving the Royal Society a compact instrument so striking that his name quickly reached London's scientific elite. Recognition brought trouble almost immediately, because Robert Hooke and other critics challenged his theory of light and color, and Newton, stung by contradiction, retreated into silence with a bitterness that revealed how fragile his public confidence could be. During years when outsiders saw only an elusive scholar, Newton filled private manuscripts with studies of alchemy, biblical chronology, prophecy, and hidden correspondences, pursuing truth across boundaries modern disciplines would later separate but which his restless mind still treated as connected. Everything changed in 1684 when Edmund Halley asked what path a planet would follow if attracted by a force that weakened with distance squared, and Newton calmly answered that it would move in an ellipse, then disappeared into work that became the Principia. Writing the Principia demanded extraordinary concentration, because Newton had to transform scattered insights into rigorous demonstrations while navigating Hooke's claims, financial worries at the Royal Society, and the pressure of explaining a universe with mathematics severe enough to convince the sharpest critics. When the book appeared in 1687, it announced 3 laws of motion and the law of universal gravitation, establishing a framework in which terrestrial mechanics and celestial motion finally obeyed the same disciplined principles. With that achievement, Newton did something almost unimaginable to earlier centuries, replacing a fragmented cosmos with one intelligible through calculation, where comets, tides, pendulums, projectiles, and planets all became episodes in a single mathematically ordered drama. His authority soon extended beyond scholarship, and after political change in England he moved into public service, eventually becoming Warden of the Mint in 1696, where the secluded philosopher entered the gritty world of clipped coins, forgery, and national finance. At the Mint, Newton applied the same cold persistence that had served his science, supervising recoinage, mastering technical details of metallurgy, and personally pursuing counterfeiters through London's underworld with a prosecutorial intensity that startled anyone expecting a merely abstract thinker. By the early 18th century he was master of the Mint and president of the Royal Society, yet triumph carried shadows, because the bitter dispute with Gottfried Wilhelm Leibniz over who had first developed calculus hardened into an international feud that stained both men's reputations. In 1705 Queen Anne knighted Newton, turning the once obscure farm boy into Sir Isaac, a symbol of English intellect and state prestige, though beneath the ceremony remained a private man marked by old suspicions, strict self-command, and periods of profound inner strain. Even in old age he never fit the simplified image later generations preferred, since he continued studying scripture, prophecy, ancient chronology, and alchemical transformation with the same seriousness he had brought to mechanics, convinced that creation formed a deeper puzzle than physics alone could solve. When Newton died in 1727 and was buried in Westminster Abbey among the nation's greatest figures, Europe honored not only a remarkable scholar but a thinker whose methods had permanently shifted the terms on which nature itself could be questioned. Newton's greatness did not come from passive genius descending like lightning, but from disciplined attention, fierce memory, repeated revision, and a willingness to pursue one difficult question for years until a pattern emerged sturdy enough to survive criticism. At the same time, his life warns that intellectual power does not automatically bring wisdom of character, because the same intensity that produced immortal science also fed secrecy, rivalry, and wounds he never fully learned to heal. What endures most is the example of a mind that looked at common things, light in a room, fruit in an orchard, numbers on a page, and discovered laws vast enough to connect human thought with the structure of the cosmos. If Isaac Newton's journey stirred your curiosity, like this video, share your favorite moment, and subscribe to Great Minds of Humanity for more cinematic stories about the people who changed the world by learning how to question it.